In the vast silence of the cosmos, where secrets linger beyond human reach, the James Webb Space Telescope has pierced the veil of an interstellar intruder. Designated 3I/Atlas, this enigmatic object hurtles through our solar system, harboring anomalies that defy explanation. What if the signals detected within its icy core are not mere echoes of the universe, but whispers of something alive? See the cold expanse of space, where rogue bodies drift untethered from any star. 3I/Atlas first appeared as a faint streak across astronomical surveys. Discovered in late 2024 by ground-based telescopes scanning the outer reaches, this object was quickly classified as the third confirmed interstellar visitor to our solar system, following Oumuamua and Borisov. Unlike its predecessors, 3I/Atlas exhibits an elongated trajectory, suggestive of origins in a distant, unknown stellar system, possibly ejected during a cataclysmic event billions of years ago. Its composition, inferred from initial spectral analysis, reveals a mix of volatile ices, organic compounds, and metallic traces that hint at a complex formation history. As astronomers tracked its approach, subtle irregularities in its rotation and outgassing patterns raised early suspicions, deviations that could not be fully attributed to solar heating alone. The object's size, estimated at several kilometers across, conceals a dense core shrouded in a coma of sublimating gases, creating an aura of mystery. Scientific teams worldwide mobilized to study this cosmic nomad, employing multi-wavelength observations to peel back its layers. Yet, as data accumulated, patterns emerged that challenged conventional models. Rhythmic fluctuations in brightness and unexpected emissions in infrared bands. These anomalies suggested internal processes far more dynamic than inert rock and ice. The stage was set for the James Webb Space Telescope to turn its gaze upon this intruder, promising revelations that could rewrite our understanding of the universe's hidden travelers. If these fluctuations are not random, but deliberate signals from within. With its unparalleled infrared sensitivity, the James Webb Space Telescope was repositioned in early 2025 to observe 3I/Atlas as it neared its perihelion. Deploying its suite of instruments, including NIRSpec and MIRI, Webb captured high-resolution spectra that penetrated the object's hazy envelope, revealing thermal gradients and chemical signatures invisible to other observatories. Initial data streams showed elevated levels of methane, ammonia, and complex hydrocarbons, compounds often associated with prebiotic chemistry in extreme environments. Astronomers noted anomalous heat sources emanating from the core, inconsistent with radioactive decay or external influences alone. As integration times extended, Webb detected faint, periodic modulations in the infrared emissions, resembling patterns observed in biological systems on Earth, such as metabolic cycles. Collaborative efforts with NASA's astrobiology divisions analyzed these readings, cross-referencing them against databases of known cometary behaviors. The telescope's imaging capabilities unveiled structural features, fissures in the surface ice that appeared to vent gases in synchronized bursts, suggesting an internal pressure buildup. Skeptics argued for abiotic explanations, like subsurface cryovolcanism triggered by tidal forces, but the precision of Webb's observations painted a more intriguing picture. The data hinted at organized activity, as if the object were responding to its environment. International space agencies convened emergency panels to verify the findings, amid growing speculation in scientific circles. This detection marked a pivotal moment, transforming 3I/Atlas from a mere curiosity into a potential harbinger of extraterrestrial phenomena. Yet, could these modulations be the first evidence of life adapting to the void? Living deeper into the spectral data from James Webb, scientists uncovered biomarkers that sent shockwaves through the astrobiology community. Elevated concentrations of amino acids and nucleotide precursors were identified in the outgassing plumes, materials essential to the building blocks of life as we know it. These organics, preserved in the object's frozen matrix for eons, suggested a panspermia scenario where life-seeding elements traverse interstellar distances. Thermal imaging revealed hotspots within the core, maintaining temperatures conducive to liquid water pockets, a prerequisite for biological processes. Comparative studies with Earth's extremophiles, such as those in Antarctic ice or deep-sea vents, drew parallels. The detected rhythms mirrored circadian-like cycles, potentially indicating metabolic activity shielded from cosmic radiation. Hypotheses emerged positing microbial colonies, or even more complex organisms encased in cryogenic hibernation, awakened by solar proximity. Rigorous modeling simulated the object's journey, estimating exposure to interstellar radiation that could mutate or preserve such life forms. Peer-reviewed analyses debated the chirality of detected molecules, favoring biological origins over abiotic synthesis. As data resolution improved, faint biosignatures, akin to chlorophyll absorption lines, appeared in the spectra, challenging the boundaries of detection thresholds. This chapter explores the methodological scrutiny applied, from signal-to-noise ratios to contamination controls, underscoring the gravity of the claims. The implications ripple outward, questioning the ubiquity of life in the cosmos and our isolation within it. But if these are indeed signs of life, how did they survive the interstellar abyss? Probing the heart of 3I Atlas required advanced computational simulations to interpret Webb's data, modeling the internal structure as a labyrinth of ice caverns and rocky strata. Seismic inferences from rotational wobbles suggested hollow voids where pressurized environments might harbor ecosystems. Chemical disequilibria in the emissions pointed to ongoing reactions, possibly enzymatic, fueling energy cycles independent of sunlight. Astrobiologists hypothesized symbiotic microbial communities, drawing parallels to Earth's hydrothermal vents, where chemosynthesis thrives in darkness. Isotopic ratios of carbon and nitrogen deviated from solar system norms, implying an extrasolar birthplace with unique evolutionary pressures. Efforts to correlate these findings with previous interstellar objects revealed disparities. While Oumuamua showed no such activity, 3I Atlas's dynamism suggested it as a rare, active wanderer. International collaborations employed machine learning to filter anomalies, isolating patterns that evaded natural explanations. Speculative theories proposed engineered biology, artifacts of an ancient civilization embedded in the object for cosmic dissemination. The chapter examines the rigorous peer review process, highlighting debates over false positives and the need for corroborative missions. As layers of data unfolded, the core's opacity frustrated complete understanding, with magnetic field distortions hinting at metallic inclusions or bioelectric phenomena. This investigation underscores the limitations of remote sensing, yet amplifies the intrigue of what lies concealed. What hidden mechanisms could be orchestrating this internal symphony? Amid the excitement, scientific rigor demands exploration of non-biological interpretations for 3I Atlas's anomalies. Geochemical models propose abiotic catalysis in the core, where exotic ices under pressure generate heat and gases through serpentinization-like processes. Critics point to instrumental artifacts in Webb's data, such as cosmic ray interference or calibration drifts, potentially mimicking biosignatures. Comparative astrophysics draws from cometary nuclei like 67P Churyumov-Gerasimenko, where outgassing creates illusions of activity. Exotic physics hypotheses include dark matter interactions or quantum effects amplifying thermal emissions. The chapter dissects these counterarguments, evaluating their probabilities through Bayesian analysis and simulations. Proponents of life detection counter with the specificity of molecular handedness and rhythmic consistency, which strain abiotic models. Debates in journals escalate, with calls for independent verification using other telescopes like Hubble or ground-based arrays. Environmental factors, such as interstellar medium contamination during transit, are weighed against the purity of detected signals. This balanced inquiry reveals the tension between paradigm-shifting discovery and conservative skepticism, emphasizing the high stakes of misinterpretation. As evidence mounts on both sides, the object's trajectory carries it further, limiting observation windows and intensifying the urgency. But if none of these explanations suffice, what unimaginable truth awaits? The detection within 3I Atlas challenges foundational assumptions about life's origins and distribution. If confirmed as biological, it bolsters the panspermia hypothesis, suggesting life is not Earth-centric, but a cosmic commonplace, seeded across galaxies via such wanderers. Astrobiological paradigms shift, prompting re-evaluation of habitable zones and the potential for interstellar migration of organisms. Philosophical ramifications emerge. Are we descendants of similar visitors or observers of an alien lineage? The chapter explores interdisciplinary impacts, from evolutionary biology to exoplanet research, where similar signatures might lurk undetected. Policy discussions arise in space agencies, advocating for protocols on potential biohazards from interstellar objects. Technological advancements spurred by this event include enhanced spectrometers for future missions, aiming to intercept and sample such bodies. The revelation fosters global unity in scientific pursuit, yet sows seeds of existential unease, reminding us of our vulnerability in a populated universe. As 3I Atlas recedes, its legacy endures in accelerated research programs, scanning for siblings among the stars. This pivotal moment redefines our cosmic narrative, from solitary explorers to participants in a grand, living tapestry. Yet, what other interstellar messengers might already be approaching, unseen? With 3I Atlas fading from optimal view, the scientific community pivots to future strategies for validation. Proposed missions, such as rapid response interceptors equipped with mass spectrometers and drills, aim to rendezvous with similar objects. Upgrades to Webb and successors, like the Nancy Grace Roman Telescope, promise finer resolutions for distant analyses. Ground-based initiatives, including SETI integrations, scan for intelligent modulations within the signals. The chapter outlines these endeavors, detailing engineering challenges and timelines amid budgetary constraints. International accords form to share data, mitigating geopolitical tensions in the face of universal significance. Simulations predict the object's return path, offering centuries-distant opportunities for direct study. Meanwhile, archival reviews of past transients seek overlooked precursors, potentially unveiling a pattern of interstellar incursions. Ethical considerations surface. Should we attempt communication or observe passively to avoid contamination? This forward-looking pursuit embodies humanity's relentless drive to pierce the unknown, transforming speculation into empirical pursuits. As instruments evolve, the threshold for detecting life lowers, heralding an era of astrobiological breakthroughs. But will confirmation arrive in time, or will the cosmos guard its secrets forever?